we present a framework for semantic video synthesis with long-term consistency. Here we show the synthesized results by our network on various datasets, including mannequin, scannet, and cityscapes. Note that the results are temporally stable and realistic. Moreover, they all exhibit what we call world consistency, which means that when we revisit the location we visited before in the synthesized world, the output frame should still be consistent with the first visit. Compared with bit-to-bit, our method can not only generate higher quality results, but also consistent frames when we revisit the same subject or location we visited before. To further verify our idea, we built a virtual 3D world using the UE4 engine. We then use the engine to render semantic inputs and pass them to our network to synthesize the output frames. Moreover, we can demonstrate the world consistency using a closed loop in the virtual world. When we make a circle and go back to the original location, the render frame can still remain the same as the first frame in the sequence. Previous methods like bit-to-bit generate each frame sequentially based on only past few frames. While this reduces flickering in the output video, it fails to maintain long-term consistency. Here we apply it on a sequence where the camera revisits the same subject in the first and the last frames. Since the memory is gone during the revisit, the long-term consistency is also lost. Note that the man is in red shirt in the first frame, but becomes in white shirt in the last frame. Instead, our framework ensures long-term stability by conditioning on all past generated frames. During synthesis, we first construct a point cloud from the past frames, and generate each frame by looking at this point cloud. After each frame is generated, the point cloud will also be updated. Since the conditioning is on all past frames, we are able to maintain long-term consistency. Note that the man is now in red shirt in both the first and the last frame. For our network architecture, we first encode the previous frame using an image encoder, then feed it to our generator, which consists of a series of multi-spade blocks. The multi-spade block contains multiple spade operations. We first embed the input labels and feed the features in the corresponding layer to the first spade layer. Next, we warp the previous output using optical flow and again extract features from it for the second spade layer. Finally, we project the constructed point cloud to obtain a guidance image and apply it in the third spade layer. This ensures that our output respects all three things: the input labels, short-term consistency, and long-term consistency. Thank you. Please find our code on our website.